Okay, it is time for some fraction work. Hello everyone, how you doing? We're going to talk fraction work because it is a really old skill. I'll call it old. When I say old, I sort of mean, basic, because it's something that you were introduced a long time ago. And we're going to break this one down in terms of appetizer, main course, dessert. Now, what do I mean by this? Appetizer is going to kind of set the stage. The main course is going to be like, what am I actually teaching you? The dessert is, I don't know. I mean, that just goes at the end of the meal. I guess some people eat dessert. So let's start off with the appetizer, which is laying down the foundation of the fraction work. I want to give you pretty much the simplest way of understanding a fraction. What is a fraction? You'll also hear this word in some cases called ratio. When you see the word ratio, I also want you to think that that's just kind of a fancy math word for a fraction. All right. It's not the same thing as a fraction, but it can always be represented by a fraction. And I'll probably have a video on ratios later so that we can get into that a little bit more closely. But a ratio or a fraction can be represented by a number on top and a number on bottom, right? We call this the numerator and we call this the denominator. But what I'm going to do is I'm going to help you use a really simple to understand analogy on how you should think of a fraction. So you should always think of a fraction if you're having trouble with like doing some abstract stuff with the fractions. You should think of the numerator as cookies. It's the number of cookies. Okay, so we have some cookies. I mean, who didn't love cookies as a kid? Who doesn't love cookies? Some people don't, but most of us understand that cookies are tasty. Most people understand that. And the denominator is going to be the number of people that we have. So what we're going to be doing is we're going to be evenly distributing a number of cookies to a certain number of people. And that already allows us to take into consideration some interesting mathematical concept here, sort of useful, is that if you have 0 in the numerator and some non-zero number in the denominator, that's the equivalent of having 0 cookies and 4 people to give cookies to. Or let's say 4 people who want and expect to receive cookies. Now, how many cookies is each person going to get? Shouldn't take you that long to realize that nobody's getting any cookies. In fact, it doesn't matter how many people there are, as long as there are not 0 people. We'll talk about that in a moment. But if there's any number of people, even if there's just one person, right? Let's say you're home alone and you're like, oh, awesome, I'm going to go eat some cookies. I'm just one person. So all of the cookies that are in this household can be consumed by me and only me. But you get to the cookie jar and there are 0 cookies in the cookie jar. Well, how many cookies is each person going to get? 0. You're going to get 0. So the moral of the story is whenever you have 0 in the numerator of the fraction, the overall value of the fraction is 0. Okay, let's take a look at a little more interesting case. What if we have 0 people? Now this gets kind of philosophical, but math gets kind of philosophical at a deep level. So let's say we have 3 cookies and 0 people. Well, then the question, how many cookies does each person get, becomes very weird, becomes very peculiar. In fact, it becomes effectively impossible to answer this. How many cookies does each person get? What do you mean each person? There are no people. How could we possibly have cookies if there are no people? So this is going to be undefined. It does not matter how many cookies we have, whether it's 0 cookies or whether it's 25,000 cookies. If we have nobody to give them to, the question, remember the question of how many cookies does each person get, this question is sort of illogical. It just doesn't make sense. And therefore the answer to the question is undefined, because there are no people. In fact, I'll even put each in like a quotation marks, because this is theoretically having some people, but in this case we have no people. Remember, when we're evaluating a fraction, we're basically answering the question, how many cookies, which is the numerator, does each person get? So we're dividing those cookies by some people. Okay, so this allows you to understand some of the basics behind fractions. And one other thing that I want you to understand is that we can reduce these fractions, which you probably remember to do. For example, if I say I have 6 cookies and 2 people, you can do the math. How many cookies does each person get? Again, we're trying to divide these things evenly. So the key with understanding fractions and division work is that you have like an even division going on. We're evenly distributing them. It's not like, oh, the bigger guy gets a little bit more cookies and the smaller guy gets a little bit less cookies. No, we're thinking about this completely fairly, as if the people were just identical and had no reason to get any more cookies than anyone else. This would be the same thing as 3 cookies for every 1 person. Now, I don't want you to think that all we did was, eliminate 3 cookies and also eliminate 1 person, but what we've done is simplified the situation. And this is where the idea of a ratio comes in. The ratio is the same because the ratio is the simplest, most reduced form, as long as we still have whole numbers, is the reduced form of a fraction. And so 6 cookies to 2 people is the exact same thing as if we had like 12 cookies for 4 people, right? You notice that you could multiply the top and bottom of a fraction. And what that would do is that would keep the same ratio because the same ratio on top and bottom. It's the same number of cookies per person is there. But all we're doing is we're adding more people and more cookies proportionally. That's the word that we would use there. Okay, and so a really important thing here is that you can only add portions which have the same number of people considered, right? I can't say, what's 2/3 plus 4/5 and simply add along the top and add along the bottom. That is not how this works at all, because you have to think again about what this represents. This is the amount of cookies that each person of 3 people would get when there are 2 total cookies, and the amount of cookies each of these 5 people would get when we have a total of 4 cookies. Now, there's not the same amount of people there, so we are not going to be adding things like that. What we could add is we could add something like 2/7 plus 3/7, because we have the same amount of people in both of these scenarios. We have 7 people. And so we can say, all right, we have a group of 2 cookies to distribute amongst the 7 people, and we have a group of 3 cookies to also distribute amongst 7 people. And so we could add the total number of cookies. We're not adding the people. There's still only 7 people. Understand what I'm saying? The denominator does not get added because that's just describing the number of people receiving the cookies. That doesn't change. All we're doing is adding more cookies to the equation. And sorry if you're like triggered by me using cookies as an analogy, or if you're hungry. If you're hungry, go eat something healthier than a cookie. This is just for purely educational purposes. It's not to like stir up some hunger. Okay, so we have 5 out of the 7 cookies. See how we were able to do that? Because we were talking about the same group of people, the same group of 7 people. Now, that's going to require us to have this common denominator whenever we're trying to add fractions together. So we need a common denominator. There we go. All right, so now on to the main course. That was the appetizer. We were just talking about fractions a little bit, but now we're going to be talking about operations with fractions. And operations with fractions are interesting because the addition and subtraction is more tedious, whereas the multiplication and division is less tedious. As we just saw with adding fractions, you have to have the same denominator. Otherwise, we're talking about 2 different groups of people, and we cannot talk about their portions of cookie the same way. How do we get the same denominator, though? That's quite interesting here. So if we want to add or subtract fractions, we need to find the least common denominator, or you can just find the common denominator, but then it will require you to reduce fractions potentially at the end of your problem. So let's see the best method for this, or the simplest method for this. If we have that 2/3 and 4/5 that we're trying to add together, we can instead use this concept of a ratio to artificially increase the number of people that we're talking about to match. So here's what I can do is I can say, all right, this denominator needs to be something looking more like 5, and this other denominator, which I'll circle rather than square box, needs to be something looking more like a 3 rather than a 5. So what can we do? Well, we can multiply both of these fractions using proportionality. I can multiply this one by 5 over 5, and I can multiply this one by 3 over 3. Now notice this does not change the value of the fraction, because if I just simply multiply the number of cookies and multiply the number of people, it has the same ratio. There's the same amount of cookie per person. But what I'm simply doing is making the group larger so that I can imagine how many cookies it would take to give 15, in this case, people, to accommodate 15 people. And then in this case, I also have multiplied the number of cookies and the number of people by 3, because 4 cookies for 5 people is the exact same amount per person as 12 cookies for 15 people. And now I can gladly add these fractions together. I have groups of 15 now, which means that I can add the total number of cookies here. So we have 10 cookies for 15 people and 12 cookies for 15 people, for a total of 22 cookies for 15 people. That's how we add fractions. I know this seems really basic, but I want you to absorb this concept so that you can use the same concept when we have variables in the fractions. I'll just give you a preview of what that's going to look like. If we have something that's like 2x over x minus 3 plus x minus 1 over x plus 5. Now these are a little more complicated because we don't even know the exact number of people or the exact number of cookies that are being involved here. But we use the exact same preparation, the same setup. We want to make sure that the number of the number of people are the same size group. So what we would have to do is we would have to multiply using proportionality by x plus 5 over x plus 5. And that takes some work to do. We're not going to go into that too much. And over here, we're going to have x minus 3 times x minus 3. So by doing that, on the top, we will end up having a certain amount of cookies for the same size group of people on the bottom. You see how that's going to achieve the same denominator, which represents the number of people who are receiving cookies, and then we'll be able to add things together using the combined like terms method and such. Again, we're not going to focus on the execution of that. You could try it if you'd like, if you're already comfortable with algebra and multiplying binomials with variable expressions. So you can go ahead and do that. In fact, that's probably a fun exercise to have done. Up a little star here so that you can solve it if you'd like to. But that was just getting the vibe of adding fractions. Same thing happens with subtracting fractions. We want to have the same denominator, and you would carry out the same process there. Now let's talk about the easier processes, the easier operations, which are multiplication and division. Now, multiplication and division are easier because you don't need to have a common denominator for this. So multiplying would look something like, 4 over 3 times 2 over 7, something like that. We have a fraction multiplied by a fraction. And now it doesn't really matter if we have the same number of people, because we're not trying to add the cookies together. We're trying to actually combine the number of groups that we have. And therefore we can group together the number of cookies and group together the number of people separately. And so multiplying fractions really is just as easy as multiplying directly across, even if I had multiple fractions being multiplied together. So this would just be 8 over 21. Remember to always simplify anything on the top with anything on the bottom. So if you can divide a common factor out of the top and bottom using a proportionality factor or a common factor, you can reduce this fraction into a more simple ratio. Let's take a look at where that might be relevant. Let's say we have 8/3. Put example 2 so that it's clear that we're not doing that example anymore. 8/3 times 4 over 7 times 15 over 16. Now, this is equivalent to 8 times 4 times 15 over 3 times 7 times 16. But there's two issues with working that out without simplifying. The first issue is that the numbers are bigger, and so you're more likely to make a mistake, or it's maybe just more difficult and more time consuming for you to do because the numbers are bigger. If you're using a calculator, which I really think you shouldn't at this level, if you're using a calculator, it won't be difficult to deal with. You'll just bloop, 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 type things into the calculator, but you won't be understanding this concept which I'm trying to show you right now, which is that if you were to simply multiply these across, let's see what you would get. I'll do them quickly. Pretty good with calculation. 480 and 336, these are big numbers, and they happen to have common factors, more than one common factor. And so I would have to spend time dividing them both by 2, or dividing them both by 3, or dividing them both by something to try to reduce the value of the fractions. Now, if you do that, you will get the right answer, but it requires more steps. And the more steps you do, the more time you're spending, which means that you take longer, but it also means that you have more opportunities to make a mistake, which is not good. So let's now reduce these fractions. We notice that 8 and 16 clearly have common factors because 8, in fact, is a factor of 16. So 8 is just 8 times 1, and 16 is 8 times 2. So we can go ahead and divide these things and reduce them down. So this turns into a 2. Any other common factors? Yeah, actually, the 2 is a common factor with the 4. So 4 is 2 times 2, and 2 is just 2 times 1. So this is going to cancel, and will leave us with a 2 on top. And then let's cancel these odd numbers here. Not that all odd numbers cancel, but these ones happen to have a common factor of 3. 15 is 3 times 5, and 3 is just 3 times 1. So this will be 5 instead of a 15. And this technically turns into a 1, but in math, we don't even write it, because if you're going to multiply by a 1, what does that do? Nothing. It doesn't do anything. It just leaves the numbers that you're multiplying. So now we could just reduce this all to 2 times 5, which is 10 over 7. Way easier. Way easier. So this is the simplified fraction. Like I said, you could get that from here if you were to divide both by 2 and then divide both by 3, or, take your time to do that. But this is a lot easier. And so I think you'll see that all the work that we do in adding and subtracting fractions really doesn't translate to when we're multiplying and dividing fractions. Multiplying and dividing fractions is a way less stressful experience, and you get to kind of chain them together. See, we have 3 fractions. You kind of just like push them all together, blob them all together, and then you can cancel anything which has a common factor. In other words, kind of like we're dividing these things. So I kind of did like 16 divided by 8 leaves a 2, and then I did 4 divided by 2 leaves a 2. So like the bigger number prevails. There's going to be stuff on the top or on the bottom, depending which is the bigger number. Here we did 15 divided by 3 is 5, so I left 5 on top. And that's a really easy way to multiply fractions. Now, let's talk about dividing fractions, because dividing fractions maybe not very intuitive. It's kind of weird what we have to do. Dividing and multiplying really aren't that different, as long as you understand that when you flip a number, you're basically doing the opposite of multiplying it. So if I were to say, okay, 4 divided by 3, that's 4 people for 3 cookies, right? 4 cookies for 3 people, right? That's the same thing as saying 4 over 1 times 1 over 3. So I'm trying to find 1/3 of 4. That's what you do when you divide something evenly into 3, is you turn it into thirds. That's what a third means. A third means if you put 3 of these pieces together, you get a whole. So in order to get a whole 4, you would put 3 of these pieces together. And doing this, you simply just multiply directly across 4/3. So what did I do there? I changed this 3. I flipped it into a 1/3. And then I changed this division sign, and I turned it into a multiplication sign. You could use an X if you want to for multiplication. The reason why I didn't do that is because when you're in algebra or higher levels of math, like when you start getting to pre-calculus and calculus, we use X as the most common letter to be used for a variable. And you might not want to get confused with that. It might look like 4 over 1 times x and then times 1/3. Okay, so we put a dot there, it just represents multiplication. All right, let's look at something a little more complicated. If we have something like 2 over 9 divided by 5/3. 2/9 divided by 5/3. Now, one thing to notice, I want you to be aware constantly of what you're doing, right? I don't want you to just follow the steps and then you get the right answer and boom, you have no way of understanding if it's a correct answer, or you follow the steps religiously or perfectly, so you figure it is the right answer. But put it into context, what we're actually doing. This here, this is larger than 1. How do I know that? Because the top number is bigger than the bottom. Think about it. You have 5 cookies and 3 people. Each person's going to get more than 1 cookie, right? They're not going to get 2 cookies. That would require 6 total. They're going to get more than 1 cookie. So we know this is larger than 1. See how that analogy really helps pretty quickly? I think people can understand visually what's going on when you consider cookies and number of people, right? We have more cookies than we have people, so if you divide it and distribute the cookies, everyone will just get some more than 1. Well, what happens when you divide by more than 1? You should get a smaller number, so we should end up with a smaller number than 2/9 at the end of this. Let's carry out the process now and see that we do get something smaller than 2/9. Flip the fraction, switch the division symbol, and let's use our method of reducing. 9 is 3 times 3. 3 is 3 times 1. So there's another 3 left here. And this is going to give us 2 over 10. It should make sense that this is smaller than 2 over 9. Why does it make sense that it's smaller? Because think about your cookies and people again. If we have 2 cookies and 9 people, then everyone's going to get, a little piece of cookie, just a little bit. But if we have 2 cookies and 10 people, each person's going to get less because we have the same amount of cookies, but more people to give them to evenly distribute them to. So that's an example where you can use the cookies and people analogy to really clearly help you out in understanding not just how to work with fractions, but how to compare them as well, how to compare if one is more than the other. So that's one way to do it. Now let's look at the dessert. What do I have planned for dessert? Think about what your favorite dessert is. Maybe you had your favorite dessert around the holidays recently. So dessert, what do we have for dessert? Well, for dessert, we have this comparison method. We're going to compare fractions. So if we want to compare which fraction is more than another, it was really easy to do it when we had the exact same numerator, or it's really easy to do it if we have the exact same denominator, because you're comparing different numbers of people for the same number of cookies, or comparing different numbers of cookies for the same amount of people. For example, it's very clear that 3 over 4 is greater than 1 over 4. If there are 4 people and 3 cookies, we're all getting a lot more than if there were 4 people and just one of those cookies. And we're assuming the cookies are all the same size. We don't have to get crazy with it. Don't overcomplicate it. I'm making this very simple for you for a reason. And just like we saw earlier, that 2/9 is going to be greater than 2/10, and that's because we have the same number of cookies this time, but different numbers of people. So whatever group has less people, but the same number of resources to distribute them, each person's going to get more of the resource. But what if they're not the same numerator or denominator? How do we compare fractions? Well, it's very simple here. If we want to know what's more, 4/7 or 7/10? Sorry, 5/7 or 7/10. Let's make it a little bit closer, shall we? So 5/7 or 7/10, which one is greater, which one is less, which one are they equal maybe? Who knows? How do we figure that out? Well, the easiest thing to do is to just multiply this one by 10 over 10. And I'll show you a shortcut to this. That's kind of the dessert part. And we're going to multiply this one by 7 over 7. Why is that? Because I can make the denominators the same, similar to how I did that when we were adding fractions, right? I can make the, where did I do that? Here it is. we can make the denominators the same, and then we're talking about the same amount of people, and we're only comparing the number of cookies. That is a great way to do it. It's a fabulous way to do it. So let's go ahead and multiply those. That's going to be 50. Now we have 50 cookies for 70 people. That's the same ratio as 5 cookies for 7 people. But what we've done is we've increased the group size, and we're also going to increase the group size here on the right. So that's 49 over 70. So both groups now have 70 people, but the proportion of cookies per person is the same. And now we can just compare the tops. So 50 cookies for the 70 people is greater than 49 cookies for the 70 people. And so this trick of just sort of multiplying the denominator up and multiplying this denominator up, perfectly valid. In fact, we don't even need to look at the denominators anymore. I'm doing it because I'm keeping the fraction the exact same, but what we're really comparing once we do this process is we're comparing the numerators now, because the process fixes the number of people in the group to be the same. And so we can find out who gets more per person, who gets more cookie per person, which group gets more cookies per person. We can figure that out by simply tracking the number of cookies now, because we've artificially created the same amount of people. So let's do that in another exercise here. Let's take a look at, and look at how close it was. I made it really close. So 50 over 70 is just a little more cookie than 49 over 70, to where you probably wouldn't even notice the difference if you were like handed the amount 5/7 of a cookie and someone else were handed 7/10 of a cookie. It would probably look exactly the same to the naked eye, but someone's getting the better end of that. Okay, so let me give you one to try. Let's say 23 over 9 compared to 86, let's say like 22 or something. Oh, wait, no. I meant to say like 29. Yeah. So what do you think? What do you think? Which one is bigger? You could take a guess. Go ahead and take a guess. In this one, you do want to check to see if there are any ways to simplify the fractions first, because these are kind of larger numbers. But I used some prime numbers here. 23 is prime. 29 is also prime. 9 is not prime. But the fact that 23 and 29 are prime means that their respective numerator and denominators are not going to have any common factors to reduce these at all. So we're going to have to just do the method. We're going to multiply the 29 over here, right? We want to see which one is bigger, smaller, or are they equal. We're going to multiply this 29 over here, and we're going to multiply this 9 over there. So let's go ahead and multiply 23 times 29. I want you guys to really work this out. Write this out if you have to. I don't care if you have to write this out. I don't care. I want you to do it. If you have to do it like that, that's totally fine. Not everybody's a freaking human calculator, and that's okay. There are enough of us freaks out of here, out in the world. So we're going to get 667, and on this side, well, 9 times 80 is 720, so we're already going to get something much bigger, but let's just carry it out. So let's see, 9 times 86 is going to be 774, and it's over the same denominator. I don't really care what the denominator is, but if you're interested in what the denominator is, it happens to be 261. See how they're the same groups of people. We really don't need to consider them anymore. We're just comparing the number of cookies now. And it turns out that this is more, therefore, this one on the right was more. That's some brief work with fractions. I won't always do this format of appetizer, main course, dessert. I just felt like getting kind of silly today. But hopefully that gave you a really simple and great understanding of how to work with fractions, whether it be simplifying them, whether it be adding, subtracting, multiplying, or dividing them, or whether it be comparing them, because at times you will have to compare fractions, what things are more and what things are not. Okay, so a reminder to not eat too many cookies when you're doing this kind of practice work. The cookie analogy is just for a mathematical relationship. I'm not trying to get people to be like, pounding cookies. And if someone asks, "What are you doing, Johnny? Why are you eating so many cookies?" say I'm practicing mathematics. Now, at that point, you're just practicing subtraction, which is subtracting the number of cookies from your household and probably subtracting the number of years to your life. So, don't induce your own diabetes just for the sake of practicing math. But keep your brain healthy, keep your body healthy, and you will succeed.